Today we're going to look at what an ohmic conductor is, and then we're going to look at other types of conductors, and we're going to focus on the idea that resistance is not always constant. So over at this side of the page we have an ohmic conductor. Now an ohmic conductor is something that follows Ohm's laws. So it follows this equation here where V is equal to IR, V is voltage, I is current, R is resistance. And it's usually represented by this graph here where current is on the y-axis and voltage on the x-axis, but don't be confused when the axes change. And the line going through the middle represents the resistance, while the gradient of this line going through the origin represents the resistance, or 1 over the resistance. So this is when the resistance is constant, and this is an ohmic conductor. Now we're going to move on to what happens when the resistance is not constant. We're going to look at a filament lamp. A filament lamp is a pretty used example in exams. So it will ask you to draw the graph or to explain the graph. So you have current on your y-axis, potential difference on your x-axis, and you have this sort of straight line here, and then it sort of tails off, it curves off at either end. Now, what's happening in a filament lamp is that as the resistance increases, so does the temperature. So if you think about your filament lamp as loads and loads of little electrons, as you increase the current, as you increase the temperature, you're going to get more vibrations, and those vibrations are going to increase the resistance. So as the resistance increases, your current is sort of going to tail off, and that's what it does on both ends. So this is what happens when your resistance is too big. Over here I've sort of summarised it in a few words. So an increase in heat causes more vibrations. More vibrations makes it difficult for the electrons to get through the resistor. More current means more temperature. As current flows, electrical energy is transferred to heat energy. Remember energy transfers. And then an increase in current means an increase in temperature, which means increase in resistance, so therefore a decrease in current. So think about the resistance increases here, more vibrations. When you have more vibrations, your current is going to tail off because there's such a great increase in resistance. Hopefully that makes sense. It's kind of a more complicated question in your GCSEs, but it's good to have a go at it. Okay. Moving on to another non-constant resistance is the diode. Now, remember the symbol for the diode. Hopefully you've remembered it. It's like that stop with a circle around it and a line through it all. And this is what the graph is of current against potential difference, also known as voltage. You sort of have this is in forward bias, by the way, forward bias diode. You sort of have a really strong resistance here. That's why there's very little current. And then at 0.6 volts or something around that area, you have a really big increase in current flow. So the current flows only in one direction, and this is the forward bias direction. So at 0.6 or around this area, you're going to have a massive increase in current. And that's what goes on with a diode. And that's how you represent it on a graph. Just note that this straight line here is because of the very high resistance. Okay, now we're going to look at some applications for diodes. So applications of LDRs and thermistors. This is sort of a recap of last lesson. So light sensitive circuits, LDRs are used in, and thermistors to temperature regulate, and they're very accurate and predictable, which is not the case with LDRs. So what thermistors are better at is being accurate than LDRs. Remember, LDR stands for light dependent resistor. So over here I've got some questions. I'd like you to pause the video and answer the questions. This one will be A, B, and C. Choose which one you think is right for an LDR circuit. Okay. Okay. Hopefully you've chosen that it is indeed A, because if it's dependent, it's depending on the arrows coming in. This is a light emitting, and this is a lamp. Okay. So question number 2. Again, I want you to pause the video and try it out for yourself. if the resistance of an LDR decreases, what happens to the light intensity? Will it be low light or will it be high light? Okay, I want you to pause the video and try it out for yourself. Okay, so hopefully you've unpaused now, if the resistance of the LDR decreases, then the light is going to be increased. So you're going to get high light because resistance and light intensity in an LDR circuit are inversely proportional. So hopefully you would have got that right. So it would be high light. Okay, and then I want you guys to draw a circuit symbol for a thermistor. So pause the video, try it out for yourself. I've given you 3 examples on the left hand side, so just choose whichever one you want. Okay, cool. Hopefully you've unpaused the video now, and you would have noted that for an LDR circuit, you can, for a thermistor circuit, you have sort of like that, and then it tails off like that. So hopefully you would have got that answer. Anyway, thank you for taking the time out of your day to watch my video, and I hope it helped. If not, let me know what needs to be changed. Thank you, bye!